Today we are going to talk about chemical equilibrium and its dynamism. Basically, in a very short session today, I will try to talk to you about what exactly we mean by chemical equilibrium and why do we say it is dynamic in nature. And also we will talk about how do we show that the equilibrium happens to be dynamic in nature. So for this, we are going to take up some examples here. Let's start with the conversion of nitrogen tetroxide to NO2. Basically, N2O4 at low temperatures, this is actually shown as a solid at very, very low temperature, but normally at lower temperature, it is a colorless kind of a gas. Okay, and when you bring it to room temperature, you just warm it a little. When you warm it, what happens is this N2O4 breaks down to give you NO2, and NO2 you know is a brown colored gas there. And if you want to study this conversion, what you can do is, if you just follow the so-called kinetics of this, we find that this is a sample of N2O4 which has partially been converted into NO2. And as time passes by, we find that there is more and more of NO2 is forming, and as a consequence, the color of this gas is changing from almost colorless to pale to brownish to dark colored over there. And if you study the concentration changes, this is interesting. So what you find is the concentration of N2O4 is decreases as a function of time, and that of NO2 increases as a function of time. Also, you need to understand here, this is understandable because N2O4 is reacting to give you NO2, the concentration will decrease. And NO2 is forming as a consequence of that, the concentration will increase. That's straightforward. But what's important here to note is that is the rate at which the concentration of N2O4 is decreasing and that of NO2 increasing, they are not same. This is almost double this one, which is again understandable because each molecule of N2O4 which breaks gives you 2 molecules of NO2. Okay, so that's how the curves are like this. But why I'm talking about this is we want to bring home a point here that in such a situation, what we observe, experimentally it has been observed that after a certain time, the concentration of NO2 and N2O4 become constant. They do not change no matter for how long you keep it at that particular temperature. The equilibrium, the mixture of the reactant and product stays there and their concentration doesn't change. That's one example. Let's take second example. Say example of reaction of H2 and I2 to give you HI. One molecule of H2 reacts with one molecule of I2 to give you 2 molecules of HI. Okay. Now here again we follow it as a function of time. So at, say, this is just an arbitrary example we've taken. At time t is equal to 0, so there are 8 molecules. We have shown here 8 molecules of hydrogen. These white ones are hydrogen, and 8 molecules of I2 are taken over there. These are purple ones there. Now, after a certain amount of time, 2 molecules each of these two react together. So left is 6 and 6 are left. So since 2 molecules of this combine together, they will give you 2 molecules of this, 4 molecules of HI. Okay, so that will be the composition. That's what we are showing here. So there are 1, 2, 3, 4 molecules of HI are formed there. Once we go a little further in time, we find the composition now becomes 4, 4 and 8. So since 4 molecules each of hydrogen and iodine have reacted, so you get 8 molecules of HI. And at a time T3, we find the composition doesn't change. Maybe we are at that stage where the composition becomes constant there. Let's go further. Take a look at the time dependence of the concentration. We find here that this is the weight, the concentration of HI is increasing, and this is the rate at which the concentration of H2 and I2 is decreasing. Again, we can see the difference. This is 1 mole each is decreasing and 2 moles are found from there. So this will be increasing at a faster rate than these two decreasing over there. But important again is that at a certain time, the concentration of HI and H2 and I2, they all become constant. They do not change with time. Let's take third example. This is a very famous Haber process for formation of ammonia. One molecule of nitrogen and 3 molecules of hydrogen combine to give you 2 molecules of NH3. And here again we find, if you follow this reaction and look at the concentrations as a function of time, we find that the concentration of H2 and N2. Both will decrease as a function of time. And also you note that N2 is just one molecule of N2 reacts, 3 molecules of H2 are consumed there. So this will be decreasing much faster than as compared to this one. And also since this reaction gives you 2 molecules of NH3, so the formation of NH3 will be twice as fast as the decrease in the concentration of N2. So that we can see from here. This is double. Okay. But again, the important point which I want to bring home is that at a certain point of time, the concentrations again become constant. Concentration of all the components, all the reactants and products put together, they become some kind of a constant over there. Let's go further. Take one more example. Say catalytic methanation reaction. Basically, it's formation of methane from a catalytic reaction between carbon monoxide and hydrogen gas there. Here again, we find that the concentrations of the reactants and products become constant at a certain point in time over there. So what do we say? And this, the concentration becoming constant, is referred to as an equilibrium. Okay, let's understand what do we mean by equilibrium now. Equilibrium basically refers to the state of apparent no change in the concentration of reactants and products. Let's understand this statement well. We have seen, they have taken 4 different examples and seen that in each one of them, after a certain point in time, the concentrations do not change. But mind you, I have put one word over there, apparent over there. Apparent means they appear to not change. But fact remains that they are changing. The concentrations, that means both the reactions are taking place. The reactions are, because the reactions are not stopped. When we say there's no change in concentration, it doesn't mean the reaction has stopped. Reaction is there, but it appears as if the reaction has stopped because there's no change in concentration. Okay. Also, we need to understand one more thing here. This is, I'm sure that you have learned about this in the school also. That is, equilibrium is indicated by a double arrow. That means such a state. That means when the concentrations of the reactants and product come to a certain constant value, they're said to be in equilibrium, and such an equilibrium is indicated by a double arrow there. Also, this is very, very crucial because all the 4 examples we have taken, they were of gaseous systems. And in gaseous systems, the equilibrium can be achieved only in closed systems. Because if you have seen that all these reactions have been done in a closed vessel there. If you do it in open vessel, equilibrium will never come. Because H2 and I2 react together, they give you HI, they will escape. And the equilibrium will never come. So for equilibrium to be achieved in gaseous systems, they must be in closed systems. That's very, very important there. Okay. So that is about what do we mean by equilibrium. I restate, equilibrium is an apparent no change in concentration. That means it appears as if the concentrations are not changing. Okay, let's go ahead and now ask ourselves, why does it happen that concentration don't change? Basically what happens is that in this reaction, we'll take an example here again, that of N2O4 giving you NO2. This should have been 2NO2 over there. So what happens is, now initially to begin with, as we saw the example over there, we started with N2O4. N2O4 was there. Okay, so N2O4 breaks down, decomposes. There's a forward reaction there to give you one molecule giving you 2 molecules of NO2. This should be 2 here, please keep in mind. Okay, now since the concentration of N2O4 is fairly large to begin with, and NO2 was not there to begin with in the reaction over there, at time t is equal to 0, there was no NO2. So as reaction proceeds, more and more of N2O4 gets consumed there, so its rate of decomposition, that means the rate of conversion of N2O4 to NO2, decreases as a function of time. That's how it goes, the blue line over there. On the other hand, since to begin with there was no NO2, so there was no rate of the reverse reaction there, because there was no NO2, so NO2 could not react to give you N2O4. So with time, when this reaction, forward reaction went in there, some molecules of NO2 were formed, so they could react together to give back N2O4, and this rate started increasing. So as more and more of NO2 was formed, more and more of this reaction became faster and faster. That means there are 2 competing reactions there. One, the forward reaction in which NO2 is being formed. One, the reverse reaction where NO2 is getting consumed over there. So, and this is how the rates go there, because if you see from kinetics, This reaction is a first order reaction. This is a first order decrease. The rate is decreasing because the rate depends on the first order of concentration there. As concentration is decreasing, so would the rate decrease. And here the rate depends on the second power of NO2. So as concentration is increasing, the rate increases sharply over there. And at a certain time, it so happens that the rate of forward reaction and the backward reaction become equal. What does it mean? What does it mean is the following, that the rate at which N2O4 is breaking down to give you NO2 and the rate at which NO2 is combining together to give you N2O4, the two become equal. So from outside it appears as if the concentration is not changing, but both the reactions are taking place. Okay, so forward reaction is taking place, so N2O4 is breaking down to give you NO2, NO2 is combining back to give you N2O4, but from outside that appears there is no change in the concentration because this breakdown and this formation are at the same rate. Okay, that means rate of forward reaction is equal to rate of backward reaction. Similarly, we can analyze the other three examples we have taken over there. So basically, the concentrations, the so-called state of equilibrium, which we defined as apparent state of no change in concentration, is achieved because the forward reaction and the backward reaction have same rate at that point in time. At that point and thereafter. Because it's not that only at that point the rate becomes equal. After that, rate always remains the same. Rate of forward reaction and backward reaction remain the same. So there is no change in the concentration of the reactants and products there. Let's understand this with the help of, okay, this is just a restatement there. At equilibrium, rate of forward reaction becomes that of a backward reaction, become equal to that one. Now, this should have becomes equal to that of backward reaction. Okay, there are certain errors in this. Now, what's a very important thing here? We need to know that equilibrium is not same as equal, because some students carry this misconception there that at equilibrium the concentration of reactants and products become equal. They do not become equal. It is a rate which becomes equal. The rate of forward reaction and rate of backward reaction becomes equal, and the concentration of reactant product become constant, not necessarily equal. They become constant. Okay, so that has to be kept in mind. Okay, let's go ahead. Let's go ahead and take up certain analogies to understand the meaning of this so-called. When we say that equilibrium is dynamic in nature, let's understand what do we mean by dynamism here. Let's take some examples first. This is simple, typical seesaw kind of a thing. There is a fulcrum here, and there are two masses, A and B, which are balanced. Okay. Now, because this balance comes because from the law of moments, when the first moments are equal, so they will be at balanced with each other. Similarly, we look at this balance over there, weighing balance. Now what you see is that here again there is an equilibrium there, and because the equilibrium is here because the mass on this span and this span are equal, so is true over there. Here again the law of first moments will apply over there. Now if we take this balance and keep it undisturbed, nothing will happen to this. The pans will stay where they are because there is no change happening there. They appear to be stationary, and they are stationary. Same is true over here also. They will appear to be stationary since they are stationary, because there is nothing happening over there. And these are examples of static equilibrium. They are static. Let's take another example to contrast this. Let's take this example over there. This is an escalator there. There's an escalator which is moving downwards. That means this escalator, I'm sure that we have seen an escalator in railway stations, in malls and other public places. We find that if the escalator is going downwards and this person is trying to go upwards. Now, let's think of different scenarios. Let's say the escalator is coming down at a certain speed. Say speed is X. And this person is trying to go up, and if his speed happens to be less than X, then what will happen? The escalator will pull him back and throw him down there. And for this person to cross over, the only way is that if his speed is more than this value X there. If it is more than X, so gradually it will go up and then can cross over there. Second situation ho gaya. Now think of the third possibility. third possibility is, suppose this escalator is coming down at the speed x and this person also is going up with the speed x, then what will happen? Now, what will happen is this escalator will be going down, the person will be going up, but if I see from a distance, if anybody sees from a distance, one will find that this person is just walking there only. He is not moving up, no one going down. He is just there only. It will appear to be static. It will appear to be stationary. But fact remains, we know that this person is moving, also this escalator is moving. That means this is so-called forward direction, this is a backward direction. Both the things are taking place, but from a distance it appears to be. It is an apparent state of no change, because the position of this person will not change apparently. Though he is moving, so is the escalator moving there. So that is the meaning of dynamism, dynamic equilibrium there. Let's take one more example here. Similar one, this is just a conveyor belt over there, and this lady is trying to reach this door beyond this conveyor belt. Again, same thing is applicable over there. Conveyor belt is moving in this direction at a certain speed, and this lady is going in the opposite direction with certain speed over there. Here again, if her speed is less than that of the conveyor belt, the belt will throw her away. And if her speed is more, then only she can cross over. And if the two speeds happen to be same, then from a distance it will appear as if she is just running at the given place only. It will appear to be stationary. Okay, that's the second example. So this again is a dynamic situation there. Let's take third example there. So look at this. So I've got a pot which has to be filled with water. There's a tap filling that pot over there. There's another tap there which is emptying it. Now initially what happens is this water is pouring in this one, but the level is low, so the emptying will be at a slower rate over there. But as more and more water fills in there, this will become faster and faster. A stage will come at that stage, the rate at which the water is filling the pot and the rate at which water is being emptied from the pot, the two become equal. And then what will happen? The level of water in the pot will appear to be constant, not changing, because the rate at which it is getting filled and the rate at which it is getting emptied, both become equal there. This again is a state of kind of it's an analogy for a dynamic equilibrium over there. Okay, so this basically is these are the analogies for dynamic equilibrium. Let's go further and see how do we demonstrate, because this is fine. We can give analogies and try to visualize what do we mean by equilibrium, what do we mean by apparent state of no change. But let's try to demonstrate it with the help of an example there. So what we do is we take a saturated solution of sodium iodide. Okay, and it is basically, you understand what the saturated solution means. There is a solution of sodium iodide and such that there is certain amount of undissolved sodium iodide sitting in the solution there. And if you look at this one, the crystal structure of that is shown that there are sodium ions and there are iodide ions there, and in solutions also some ions are shown over there. Okay, that is one situation we have. Then what we do is we take a saturated solution of labeled NaI. That means we take sodium iodide in which some iodide atoms have been radioactively labeled there. I-137 has been used over there. So what happens now? So you have again same situation there. So you find that the solid, there are a few iodide ions are radio labeled over there, and in solution also there are both kind of ions there. Some are radio labeled, some are normal ions over there. Fine, that is number 2. What do we do next is we take this solution, saturated solution of radio labeled sodium iodide, and pour the supernatant part of this into this solution there. Mind you, there is no radio labeling in this one. We don't transfer any solid from here to here. We only transfer the liquid part there, and then the liquid part, what do we have? We have got sodium iodide solution, whereas some iodide ions are radio labeled over there. So they will all come in over there. Then what we do is we allow the system to stay for some time, and then we observe. When you observe, we find that this solid, which initially was unlabeled sodium iodide, it has got some components of iodide labeling coming over there. And this is possible only when there is an equilibrium here. there's an equilibrium between the dissolved sodium iodide and the solid sodium iodide sitting in the solution over there. So what's basically happening in this example is that there is a continuous exchange of sodium iodide. That means sodium iodide is getting dissociated from the crystal into the solution, and from the solution it is crystallizing back into the solid form. So this equilibrium is there, and because of this equilibrium, so some iodide ions which we pour from outside now actually are able to get into the solid state over there, and from solid state equivalent amount of iodide ions will come out of there. So this demonstrates that the dynamicness, that means the forward reaction and backward reaction becoming equal. That means from apparently it appears as if it's stationary, but they are not stationary. Things are taking place, and that exactly is the meaning of dynamism of equilibrium. Okay, so that's what we wanted to do today. Next we will talk about characteristics of chemical equilibrium there.